Hello everyone, let's do some math. Find the points on the surface x, y squared, z cubed equals 2 that are closest to the origin. Okay, so we have a function of 3 variables, which is equal to a constant. So this is going to define a curve in 3-dimensional space, and we want to find the points closest to the origin. So is the best way to do this to write down the distance? Yeah, okay, so what I'm going to do, I'm going to set this up as a 3-dimensional optimization problem. I'm going to write down the distance of an arbitrary point, x, y, z, from the origin. And then I'll treat the equation we're given as a constraint, and I'll try and minimize the distance. Now, of course, minimizing the distance is the same as minimizing the square of the distance. So the function I'm actually going to minimize is this one, x squared plus y squared plus z squared. And the constraint will be that x, y squared, z cubed minus 2 has to be equal to 0. Okay, so I'm going to do this. What's the best way to do this? I think I'm just going to do this with a Lagrange multiplier. At least that's how I'm going to start. So I'll introduce a Lagrange multiplier for the constraint here, and then use appropriate minimization and maximization techniques to find candidate points, x, y, z, which could be closest. Okay, so after doing this, I get a system of equations that I need to solve. I have 4 equations and 4 unknowns. 3 of these equations come from partial derivatives, and the last equation comes from the constraint itself. Lambda is an unknown here, but I don't really need to solve for lambda. I really only need to solve for x, y, and z. So I'm going to think a little bit about how I might do that. And it might just be playing around with some algebra. It looks like it might be a little bit messy, but maybe we'll be able to get to something. Okay, so I seem to have come to a contradiction here, leading me to believe I have a mistake in my algebra. I'm not going to go back and try and find the mistake. I'm just going to kind of go back to my original setup of the problem and make sure that I've written these things down correctly and derived the system of equations I need to solve correctly. So let me do that in my head kind of quickly here. Okay, another thing that I noticed also partway going through that algebra, which I'm now pretty sure is probably wrong. If I look at these 3 equations here, if I multiply this one by x, multiply by this one by y, and multiply this one by z, then these terms will change appropriately, but in all of these, I'll end up with the same expression, x, y squared, z cubed. Which I should be able to just replace with the number 2 because of the constraint. So I think that's the approach I'm going to take when I go through this a second time, rather than just trying to eliminate all these variables one at a time. Okay, so I think I've mostly narrowed this down. I did sort of do some operations here which might accidentally introduce some new solutions or something like that, but I don't think that ended up happening. So what I have here is I have the values of x squared, y squared, and z squared in terms of lambda. Sorry, not in terms of lambda. I have their values, x squared, y squared, and z squared. Now, of course, we can compute the, there might be several points here which are closest to the origin because, x can be positive or negative, y can be positive or negative, and z can be positive or negative, except I have to keep in mind in the constraint that x, y squared, z cubed is equal to 2. So it doesn't matter what sign y is, but x and z have to have the same sign because this product has to be positive. So if I list out all the possible points here, this will be 1 where all the coefficients are positive. And then what I can do, the y coefficient can be negative if I want, and then both the x and z coefficients can be negative if I want. So I have all possible combinations here that might work and keep the product the same in the constraint. So they can all be positive, or only y can be negative and the other's positive, or switch it up. X and z can be negative and y positive, or all three can be negative. Yeah, I think this will work. I would want to kind of go through this again more carefully to verify my answer. I like that, in doing this, all of the possible values of x, y, and z that it came up with, all candidate points are the same distance from the origin. So like, because these all have the same, more or less the same x, y, and z coordinates, just with sign changes, all 4 of these points are the same distance from the origin. So we don't have to worry about eliminating some of these candidate solutions. And we know for sure that they correspond to a minimum because I can find points that are, can I find points that are arbitrarily far away from the origin? I think I can, right? If I look at the constraint, just, yeah, if I choose y and z to be very, very small, then I'll have to choose x to be very, very large in order for this to hold. And the smaller y and z are, as they approach 0, x will have to approach infinity, and so that's a point that's getting arbitrarily far away from the origin. So I don't have to worry about minima or maxima or any of that kind of thing. These are definitely going to be minimizing values of the distance. Yeah, so I'm pretty confident in this, that these are all the points which give us the minimum distance on the surface. But if I find a mistake or if I have any kind of additional comments, I'll put them down in the description. Thanks for watching.